Welcome to the video for section 4.1, Solving Quadratic Equations. So in this section, if you've perused the notes, you'll know that we're dealing with 4 different techniques for solving quadratic equations. And our basic setup, any quadratic equation can be written in the form ax squared plus bx plus c equals 0. Now this is not exactly how they'll always look, but every single equation that we see in this section can be written in this form if we manipulate it a little bit, if necessary. We'll call this standard form. Because frequently we're going to want to put our quadratic equations in this form at the beginning of our solution process. So the first method involves solving by factoring, and I recommend that you go back and look at the review section of the notes, section 0.6, for just a quick discussion of some of the techniques. I'm not going to get into the details of them. I will be using those techniques. So I recommend, if you haven't seen these kinds of things for a while, if you start to get lost or overwhelmed by what we're doing in this section, go back, pause, go back and look at those, and come back to the video. So the first equation that we'll solve by factoring is 3x squared minus 3 equals 0. Now sometimes factoring will be kind of an involved process and will involve the steps outlined in section 0.6 back in the review. But sometimes it'll be a little bit simpler. So the first thing that we always want to do, if possible, is factor out any constant factor of every term. So I notice that there's a 3 present in every single term here, so I'll factor that out, and I'm left with x squared minus 1. Now if I divide both sides by 3, what is the result? Well, my 3 will be lost, and I'll get x squared minus 1 on the left, and 0 divided by 3 is still just 0. So I'm still working towards solving this equation. I still have x's. I never want to divide by x, because I could lose solution techniques, and I'll show you what I mean in the next problem. But where can we go from there? Well, if we refer back to the factoring approach, we want to factor this into binomials. My first term in each of these binomials should multiply to x squared, so I think x and x are going to be our winners. Then I want my last term to multiply to 1. And there's only one pair of numbers, whole numbers, that are going to multiply to 1, and that is 1 and 1. Now I'll pick my signs so that my middle term adds up to, notice that I don't have an x term here, so my middle term has a coefficient of 0. If this one is positive and this one is negative, that'll do the trick. Now, just to confirm, you can multiply that back out, x minus 1, x plus 1. If I FOIL those, I get x squared minus x plus x minus 1. Those x's in the middle cancel, we get x squared minus 1. So that is the correct factorization, and we'll go from there and apply the zero product property. So here I have 2 factors, a and b, which multiply to 0. If a product of 2 numbers multiplies to 0, then one of those numbers must itself be 0. So either x plus 1 equals 0 or x minus 1 equals 0. So just like back in the absolute value equations section, we end up with 2 potential solution avenues, which I then have to follow to their termination. So if I subtract 1 from both sides of this equation, I get x equals negative 1. If I add 1 to both sides of this equation, I see that x equals 1. And these are both solutions to the quadratic equation. So let me check that work. I will plug x equals negative 1 back into that quadratic. So 3 times negative 1 squared minus 3 is equal to 3 times negative 1 squared would give me just 1 minus 3. So that's 3 minus 3, which is 0. And that satisfies the equation. For x equals 1, our work is even simpler. 3 times 1 squared minus 3 is equal to 3 times 1 minus 3, which is 3 minus 3, which is 0. Now, the most we can expect to find is 2 solutions in this section. So if you find 2 solutions, you're done. You always want to verify that they are in fact solutions, because there's some tricky business going to happen in the solution process from time to time. This one was not too bad. Let's look at the next one and see what's going on there. So this equation would tend to lead you in the direction of dividing both sides by x. I'm going to avoid that for right now. The first thing I'm going to do is put this in standard form. That is, I'm going to get one side equal to 0. I'll do that by subtracting 9x from both sides. And that leaves me with x squared minus 9x on the left and 0 on the right. So now I need to factor the non-zero side. And in the sort of hierarchy of factoring, the first thing I try to do is factor a common factor out of every term. Notice that my terms here are x squared and 9x, both of which have an x as a factor. So if I factor x out, I am left with x minus 9. So again, we're in that position of having 2 factors, x and x minus 9, whose product is equal to 0. This leads me down 2 logical avenues, either x equals 0, or the other factor, x minus 9 equals 0. Well, this approach, this first possibility, we don't need to do any more work. X equals 0 is one possible solution. Now if I add 9 to both sides of our second possible equation, we see that x equals 9. I'll check both of those. Go back to our original equation. If we check x equals 0, we do that by plugging 0 in on the left, 0 squared equals 0, and on the right, 9 times 0 equals 0. And so these are equal to each other. And we have a satisfaction. On the other hand, if I plug in x equals 9, on the left I'll have 9 squared, which is 81. And on the right I'll have 9 times our x value of 9, which also gives us 81. So our left and right hand sides are equal in both cases. So let me go back and try that the naive way. If I see x squared equals 9x, and if I divide both sides by x, I'm left with x equals 9. That's only one of the 2 solutions. We lose one by dividing by x. So you never want to divide by the variable itself because that variable could potentially be 0, and in this case that is one valid possibility. So dividing by 0, even if it's symbolic, even if it's going on behind the scenes and we don't know that we're doing it, is still going to cause problems. So here we have our third quadratic equation, 20x squared plus 20x plus 5 equals 0. So I will go through the steps by the book. The first thing I'll do is see if there's a common factor in every term. Now 20, 20, and 5 are all divisible by 5, so I'll factor 5 out of each term. That will leave me with 5 times whatever's left. So 20, if I factor out of 5, I'm left with 4x squared. Again, if I factor 5 out of 20, I'm left with 4 and x. And if I factor a 5 out of 5, I'm left with a 1. Now, if I divide this equation by 5 on both sides, I lose the 5 on the left, and 0 over 5 still ends up being 0. So now we have a nice simplified quadratic equation that's going to be a lot nicer to solve than this one involving these larger numbers. This one happens to have a leading coefficient of 4 rather than 1. So I am not going to bother with the guessing and checking. I really like the AC method. So I'll take A and C, that is 4 and 1, and the product of those two numbers is 4. So now I'm going to find all of the different two-number factorizations of 4. 4 could either be 1 times 4, or it could be 2 times 2. And don't forget about the negative possibilities. This could be 1, -1, and -4, or it could be -2 and -2. Now what I'm looking for here is the pair of numbers that adds up to the middle term, that adds up to b. So which of these pairs adds up to 4? I think our second pair of numbers, 2 and 2, are the ones that we want. So what am I doing this for? Well, what I'm going to do now is rewrite this equation, replacing the 4x with this smaller version of itself. So 4x squared plus 2x plus 2x. So I'm breaking this down into two pieces. Plus 1 equals 0. And my reason for doing that is now I can factor by grouping, and there should be no guesswork involved. So the common factor of the first two terms, I see that there is a factor of 2 and x. So if I factor that out of the first two terms, I'm left with a 2x and a 1. There doesn't seem to be a common factor to these guys, so I'll just say that's plus 1, and I'm factoring a 1 out, so I'm left with everything that I had to begin with. Now I have two terms. The common factor of the first term and the second term is that quantity in parentheses, 2x plus 1. So I can factor a 2x plus 1 out of each of those. And what am I left with? The 2x and the 1. So there we have our factorization. We have to go one step further now. Since this is factored, I can apply the zero product property, which says that either 2x plus 1 equals 0, or, this is a little redundant, 2x plus 1 equals 0. Now since these are the same equation, I really only need to solve one of them to figure out what's going on with both of them. If I subtract 1 from both sides of this left-hand equation, 2x equals -1, and then I'll divide by 2, and I see that x equals -1/2. This other equation would give us the same result. So technically we found two solutions, they just happen to be the same number. We'll come back to that idea at the end of this section. Let me check those x values, and this one I'm going to do in the calculator to show you how that would work. So a little trick that I like to use with the smarter graphing calculators, if that's what you're working with. Some scientific calculators also have this feature. But you can store numbers in a given variable. So you'll notice on mine there are all these little letters on a bunch of the keys. So if I type in the x value that I think is my answer, -1/2, -0.5, I'll hit store, and then I'll select the letter x by selecting alpha x. Now what that's going to do is store -1/2 in the letter x. So when I bring that letter back up, the calculator thinks, oh, that letter and -0.5 are the same thing. So then I can just type in the left-hand side of my equation. 20x x, now I'm not using the variable x, I'm using the letter x, squared plus 20 alpha x plus 5, and that turns out to be 0. So we get our justification, our verification that x equals negative 1/2 is the solution to this equation. Now the next technique for solving quadratic equations is called the square root method. And this relies on the idea of the square root property. Now that says that if we have something of the form x squared equals a number, then either x equals the positive or negative square root of that number. So let's see a couple of equations that we can solve in that way. X squared minus 81 equals 0. We want to put this in the form x squared equals a number. Now this technique is only going to work with equations that don't have an individual variable by itself. So we need something squared and constants and nothing else. So the first thing I'll do is add 81 to both sides. So we get x squared equals 81. And then I'll square root both sides to get x equals the positive or negative square root of 81. And 81 is a perfect square, so we see that x equals the positive or negative square root of 81, which is 9. Now this one is pretty easy to check manually. It'd probably be more work to do it in the calculator. So if I check x equals 9 in the original equation, is 9 squared minus 81 equal to 0? Well, 9 squared is 81. So 81 minus 81 is 0, and we have a valid solution. X equals negative 9 is going to look pretty similar. If we plug that in, negative 9 squared minus 81 is equal to negative 9 squared still gives me 81 minus 81, which is still 0. So both of these numbers are solutions to our original equation. On the next page we have another quadratic equation, 2x squared minus 18 equals negative 2, and we'll solve it in the same way. So what I want to do is isolate the thing that's being squared, the variable term that's being squared. So to do that, I'll add 18 to both sides, leaving me with 2x squared equals 16. Then I'll isolate the x squared term by dividing both sides by 2. So x squared equals 8. And then applying the square root property, this implies that x equals the positive or negative square root of 8. And we can simplify that a little further. Since 8 is 4 times 2, we can pull that 4 outside. This is the positive or negative square root, 2 square root of 2. So that 4 comes outside, we keep the 2, and that is our pair of solutions. I'll check this one in the calculator as well, just to show you how useful that storage feature is. Let's do 2 square root of 2. Okay, that's a big weird number, but let's store that in x. So now I'm overwriting the x that I had saved before. Now I'll plug that into the left-hand side. 2x squared minus 18 gives me negative 2, so that's a winner. Now I'll do the negative version of the solution, negative 2 square root of 2, and I'll store that overwriting the x value. So now I can just bring back that entry where I said 2x squared minus 18. This time it's going to use the new value for x, which also yields negative 2. So both of these work, and we have found all of our solutions. So here we see one final equation, problem number 6 here, which does not immediately jump out as a quadratic. If you multiply this all out and get one side equal to 0 and simplify, you would see that this is quadratic. It can be written as ax squared plus bx plus c equals 0. We're not going to bother doing all of that, however, because we are going to use the square root method, but this time we're not going to isolate x first. We're going to isolate the variable term which is being squared. In this case, this expression 2x plus 1 squared. We're going to get that by itself by dividing by -5. So if I do that, I see that 2x plus 1 squared is equal to -5, dividing 25 by -5. Now I'll apply the square root property. Because I have something squared equals a number, I can square root both sides, and I see that 2x plus 1 equals the positive or negative square root of -5. Now, back in 4.0, we figured out a way to simplify this. We could write this as 2x plus 1 equals positive or negative root 5 times I. We can pull that negative outside of the radical and call it I on the outside. So now all I need to do is solve for x. I can do that by subtracting 1 from both sides. So 2x equals -1 plus or minus root 5 times I. And notice the I is entirely outside of the radical. Then divide both sides by 2. So x equals -1 plus or minus root 5 I over 2. So we're technically done. I want to write these as separate answers, however, and since I have an I here, I'll write it in the standard complex form. We could write that as -1 over 2 plus or minus root 5 over 2 times I. So our two solutions, x equals -1/2 plus square root of 5 over 2 I, and x equals -1/2 minus square root of 5 over 2 I. Now I did not mention in the last section, but you can actually use the calculator to discuss imaginary numbers. So let me show you where that is. Notice at the bottom of your calculator, down here on the decimal, the point button, just up above it there's a little blue I. So if you select that by hitting second shift I, you'll see that it returns I. Now that is in the calculator as the imaginary unit. That represents the imaginary unit. Your calculator can perform calculations using that. So let me type in my solution, -1 over 2 plus the square root of 5 over 2 times I. So that's my first x value. And you'll see that it returns this big decimal expansion. So you have -0.5 plus 1.118033989 I. Well, that 1.11, etc., is an approximation of the square root of 5 over 2. So this is exactly the same number we typed in. I will store that as x. Okay, let me clear everything out. Now if I type x, it'll deliver back to me that x value. So I'm going to use that, plug it into the original equation, -5, 2 times x plus 1, all squared. And it turns out, when that is our x value, that left-hand side evaluates to 25. So that x value worked. The other x value, if I plug that in, I will need to make a little modification. I'll go back to the earlier entry where I typed in the plus root 5 over 2 version, and I'll just change that plus to a minus, and then I will store that new x value and then I'll bring back the entry of my left-hand side of the equation, and we get 25 again. Now, if you want to confirm these by hand, it is a little bit labor-intensive. I'll show you how one of them would work. So if we do -5 times 2 times, and I'll plug in my first x value, -1/2 plus root 5 over 2i, plus 1 squared. That's my left-hand side. Now I'm going to simplify this, and hopefully when we're all done we'll end up with 25 equal to the right-hand side. So the first thing that I recognize is everything inside the inner parentheses is being divided by 2. So if I multiply that 2 in everywhere, that's going to cancel, and I'll be left with -1 plus root 5i. I still have a plus 1 left over, and so things have already cleaned up quite nicely. Now I notice that I have a -1 and a plus 1. Those will cancel with each other. I have -5 plus root 5i, which I am supposed to square. Sorry, I don't need that plus anymore. Alright, well, if I square a product, and remember order of operations, I want to perform the exponentiation before I multiply by -5. If I square the product of root 5 and I, that would involve squaring the root 5 and squaring I. So that's taking care of the exponent. Now that would give me -5. If I square the square root, we just end up with 5. And I squared, by definition, is equal to -1. So what do I really have inside? This is -5 times -5. And we know the product of -5 and -5 is 25. So the solution process, checking that answer, even though it's big and scary and imaginary, complex, if you're very careful and you follow the order of operations and distributive laws and all the properties of real numbers and imaginary numbers, then you should end up with a nice logical process that proves that your x value is a solution. Moreover, if you do go through that process very carefully and you don't end up with 25, then you know something went wrong up here in the solution process. So that is how we use the square root method. We isolate the thing that's being squared, and we isolate the constant on the other side, and then we apply the square root to both. Don't forget your plus or minus. And then if there's more solution to go, if you still need to solve for the variable, you may have a little more work ahead of you. But from there, you don't need to worry about quadratics. You'll be solving linear equations. Now, our third technique for solving a quadratic equation is called completing the square. And this relies on the nice property described on page 51, which says that if you have a quadratic of the form x squared plus bx plus the constant term b over 2 squared, this will factor as x plus b over 2 squared. So we can turn a quadratic into a perfect square trinomial if we add that term b over 2 squared. Now this relies on the leading coefficient of x squared being 1. Then we pick out what b is, divide it by 2, square it. That's what we need to add in order to make a perfect square trinomial. Now if you don't believe this part, FOIL out that right-hand side. X plus b over 2 squared, that's x plus b over 2, x plus b over 2. So that would give me x squared plus b over 2x plus b over 2x plus b over 2 squared. my middle terms, if I have b halves and b halves, I can add those. They're the same type of fraction. That's b, 2b over b, which cancels down to b, x plus b over 2 squared. So if we have this relationship between the coefficient of x and the constant, then we're in good shape to factor in this way as a perfect square. So the way that we complete the square, or solve quadratic equations specifically by completing the square, first we'll move that 5 over to the other side. Get that out of there, move the constant over on its own. Okay. Now what we need to do is figure out, first, is the coefficient of x squared a 1? So all we have right now is x squared, which means we can skip over that second step. We don't need to mess with this equation. X squared is already as it should be. So now I'm going to look at the coefficient of x. I'll take that off to the side, 8. I want to divide that by 2. So b over 2 is equal to 8 over 2, which is 4. And finally, I'm going to square that. So b over 2 squared, we know that's 4 squared, which is 16. So that's the number I need to add to both sides. So I'll add 16 to the left to make a perfect square. But in order to do that, I need to also add it to the right-hand side. Okay. So now, if you came into the room and this was the quadratic that you had to solve, you could factor it as x plus 4 quantity squared. Notice the 4 showing up again in the factored form, just like in the generic case up here. B over 2 shows up when we add b over 2 squared to the unfactored form. Okay, so we've completed the square, and now we've factored. Let me clean up the right-hand side a little. Negative 5 plus 16 would be 11. And then this equation we can solve by the square root method. So if I square root both sides, that will give me x plus 4 equals the positive or negative square root of 11. And finally, if I subtract 4 from both sides, we get x. Negative 4 plus or minus the square root of 11. So let me check one of those by hand. I'm going to check x equals negative 4 plus the square root of 11 in my original equation. So negative 4 plus root 11 squared plus 8 times negative 4 plus root 11 plus 5. That's equal to, okay, now I'm going to have a little bit of work ahead of me. I need to square negative 4 plus root 11. So let me write that out as negative 4 plus root 11 times negative 4 plus root 11. I'll go ahead and distribute the 8 in. We're going to have 8 times negative 4, so negative 32. And 8 times square root of 11. There's no better way to write that than 8 root 11. And then finally we've got the plus 5. Okay. So now I need to FOIL out those that first term. Negative 4 times negative 4 would be positive 16. Negative 4 root 11. Negative 4 root 11 from the inside terms. And square root of 11 times square root of 11 would just give me 11. Still got minus 32. I still have plus 8 root 11. And I still have a 5. So these checking processes tend to involve a lot of very careful bookkeeping. So now I need to combine similar things. Well, how many constants do I have? I have 16 plus 11 plus 5, so that's 16 plus 16, 32. minus 32, it looks like all of those cancel out, and I get 0 for my constants. And then I have negative 4 root 11, minus 4 more root 11, so negative 8 root 11, plus 8 root 11. So those cancel with each other, and turns out I just have 0. And that is exactly what we were supposed to get. So x equals negative 4 root 11 checks out. I'll do the other possibility in the calculator, although the solution process would look very similar. If I store negative 4 minus root 11 in the variable of x, and then I plug that, it turns out to be negative 7.31662479. Probably goes on pretty much forever. Let me try that. So if I do x squared plus 8x plus 5, fingers crossed, I'm hoping for 0, and that's what we get. So the negative version is also a solution. Going back to our final answer, both of those check out. So that is what completing the square is going to look like. Now we'll go through the next one a little bit quicker. We won't worry so much about the checking process, but I want to be careful and stress all of the steps involved here. So here we have another quadratic equation. This one is not written in standard form, but if we moved everything over to the left or to the right, we could write it as ax squared plus bx plus c. So what we're going to do if we want to complete the square is isolate the constant term. So let me add x to both sides. I'll write this as 2x squared plus x equals 5. Now I need to get that coefficient of x squared to be 1. So I'm going to divide everything by 2 because my completing the square process relies on that being 1. Okay, so if we write this as x squared plus 1/2 x equals 5/2, then we're in good shape to start completing the square. So right now, b is 1/2, the coefficient of x. b over 2 would be 1/2 over 2, which is 1/2 times 1/2, which is 1/4. Which means that b over 2 squared would be 1/4 squared, which would be 1 squared over 4 squared, or 1/16. This is the number that we have to add to the left-hand side in order for it to be a perfect square, and we have to add it to the right-hand side if we do that in order to keep our equation balanced. So let me add 1/16 to both sides. That results in our equation x squared plus 1/2 x plus 1/16 equals 5/2 plus 1/16. Now, since I completed the square, I can factor this as x plus 1/4 squared. Remember that 1/4 is b over 2. That's going to come back when we factor. Alright, now the right-hand side, 5/2 plus 1/16, I'll do a little side work here, plus 1/16. If I want a common denominator so I can turn this into a single number, I could write this as, well, a common denominator of 16 would be good, so let's multiply the top and bottom here by 8. So 40 over 16 plus 1/16 looks like 41/16 on the right. Okay. So this one's a little bit stranger, but we did everything exactly the same. Isolate the constant, divide if necessary to get that leading coefficient to be 1. Take the coefficient of x divided by 2, square the result, and add that to both sides of your equation. Once you've done that, you can solve the resulting equation using the square root property. So if I square root both sides, I get x plus 1/4, I get rid of the square, equals the square root, positive or negative, of 41 over 16. So x, if I subtract 1/4 from both sides, is equal to negative 1/4 plus or minus the square root of 41/16. So that's one way we could leave our answer, but generally we like to simplify things as much as possible. Negative 1/4 plus or minus, we could apply that square root to the numerator and denominator separately, so 41 over the square root of 16, which is 4.